You know that feeling, right? You're staring at a physics problem, you know all the formulas, but you just have no idea where to even start. Well, today, we're going to tackle a classic problem about elliptical orbits. And by the end of this, I promise, you won't just have an answer, you'll have a whole new way of thinking that makes these kinds of problems just click.
So this problem comes from a book that is, let's be honest, a rite of passage for physics students, i.e. Irodov's Problems in General Physics. It is legendary for being incredibly tough, but also for building a really deep understanding of the core concepts. So if you've ever felt stuck on one of these, trust me, you are in very good company.
All right, so here it is, problem 1.207. We've got a planet, we know its mass, m, and we know its closest and farthest distances from the sun, r1 and r2. And that's it. From just those little pieces of information, we need to find its angular momentum. Now, your first instinct might be to try and calculate forces and speeds at every single point, but oh, there is a much more elegant way to do this. Okay, here's our game plan. First, we'll break down the challenge. Then, we'll grab the two most important tools from our physics toolkit. After that, we'll map out the orbit to find the easiest spots to work with, set up our equations, and solve this thing. Let's get into it. So let's be absolutely crystal clear on the goal here. The only things we know are the planet's mass, m, its maximum distance, r1, and its minimum distance, r2. The whole challenge is to find the angular momentum, m, using only those three things. We have no idea what the velocities are, or how long the orbit takes, or anything like that. This is where physics gets really cool. Instead of trying to track the planet's speed and position moment by moment, which would be a nightmare, we can use two secret weapons that are just perfect for orbital mechanics: conservation laws. They let us totally ignore all the complicated stuff happening in the middle and just focus on what stays constant. Our first secret weapon is the conservation of angular momentum. Think of it like this. To make something spin faster or slower, you need to give it a twisting force, right? A torque, like pushing a merry-go-round at the edge. But the sun's gravity only ever pulls the planet straight towards its center. There's no sideways push, no twist. And because there's no torque, the planet's angular momentum has to stay exactly the same through its entire orbit. And tool number 2 is the conservation of mechanical energy. Since gravity is what we call a conservative force, the planet's total energy is totally fixed. It's kind of like having a fixed budget that you can split between cash in your pocket, that's your kinetic energy, your energy of motion, and money in the bank, which is your potential energy. As the planet speeds up, it's taking money from the bank to use as cash. When it slows down, it puts that cash back in the bank. But the total amount, that never, ever changes. All right, we've got our toolkit. Now it's time to actually use these laws. And here's the trick. We could technically pick any 2 points in the orbit, but the key to solving this problem easily is to pick the 2 points where the math becomes ridiculously simple. And here they are, those 2 magic points. The farthest point, r1, is called aphelion, and the closest, r2, is perihelion. Now, what's so special about them? Well, at these 2 exact spots, the planet's velocity is perfectly perpendicular, at a right angle, to the line connecting it to the sun. This is the insight that just unlocks the entire problem, because it makes the math for both angular momentum and energy so much cleaner. And this just perfectly shows that constant give and take we were talking about. At aphelion, when it's farthest away, the planet has the most potential energy stored up, so it's moving at its slowest speed, v1. Then, as it swings in close to the sun at perihelion, it's cashed in all that potential energy, so it has the least amount, but it's moving at its absolute fastest speed, v2. They just trade places, but the total energy is always the same. So, let's recap. We have 2 conservation laws. We have 2 strategic points. Now we just put them together. By applying each law at both points, we can create a system of 2 equations. And guess what? We have exactly 2 things we don't know, the 2 speeds, v1 and v2. This is perfect. The procedure from here is actually pretty straightforward. First, we write down that the angular momentum at both points is equal. Second, we do the exact same thing for the total energy. That gives us our 2 equations. And from there, it's just algebra. We use the first equation to get a relationship between v1 and v2. Plug that into the second equation and solve. Honestly, the most common pitfall here is just a simple algebra mistake, like mixing up r1 and r2. So just be careful, be methodical, and double-check your work. Now, we're going to skip showing every single line of algebra because, let's be real, nobody wants to watch that. But the process is basically substituting one velocity out and then just carefully rearranging all the terms. After a bit of work, all the velocities just cancel out, and we're left with this beautiful, clean, final expression for the angular momentum. And here it is, our final answer. The angular momentum, m, depends only on the things we were given at the start: the planet's mass, the sun's mass, the gravitational constant, and our two distances, r1 and r2. We found it without ever needing to know the planet's actual speed. And yes, for those of you following along in Irodov at home, this is the correct answer.
But you know what? That final formula isn't the real prize here. The strategy is. This four-step process, this is the real takeaway. For any complex system, first ask yourself, what is being conserved? Then find the points of maximum simplicity. Apply your conservation laws to build your equations and then solve. This method is like a universal key that can unlock so many problems way beyond just planetary orbits.
So that leaves us with a final thought to chew on. This strategy works perfectly for orbits, where forces and velocities are always changing. But where else could it apply? What about particle collisions, or the wild looping motions of charges in magnetic fields? This hunt for what stays constant, it really is one of the most powerful and fundamental ideas in all of physics.